Welcome to our video on the power equation and hydroelectric dams. Hydroelectric dams have played and continue to play a crucial role in the development of our society. One example of an important hydroelectric dam is the Hoover Dam down in the southwest US. Because of this dam, life in desert cities like Phoenix and Las Vegas becomes possible. Power from Hoover Dam covers areas in Nevada, Arizona, and even parts of California. Now, you might be asking yourself, how does a dam like this work? Well, let's first take a look inside the dam. Let's just say that this dam is home to a lot of turbines. There's actually 17 to be exact. And as you can see, these turbines are quite large. Now, what is the point of all these turbines? Well, in the Hoover Dam, like any hydroelectric dam, the turbines are what is used to harvest the kinetic energy of the water passing through the dam. In a basic hydroelectric dam, water passes through the intake into the penstock, where it is used to turn the turbine, which in turn creates usable energy. After the kinetic energy of the water is harvested, it is allowed to flow out and downstream.
In this example, we will be examining the Norris Dam in Tennessee. The specifications for this dam are a height of 81 meters, a rate of work done by the turbine of 100 megawatts, and a flow rate through the dam of 150 meters cubed per second. Here is a cutaway of the dam, which we can use to visualize where these specifications apply. The height is measured from the turbine, where our datum is, to top of the reservoir. The Q value, or flow rate, goes through the center of the dam and is equal to 150 meters cubed per second. Here's an image of the dam, and we will apply the specifications listed on the previous two slides to it. The datum is placed at the bottom of the dam in line with the turbine, and from there we measure up to the top of the reservoir, which gives us the height of 81 meters. The flow rate Q through the middle of the dam is equal to 150 meters cubed per second. In this problem, we will be attempting to determine two things. First, the rate of work done by the fluid, and second, the rate of work lost in the system. We can determine these by deriving a power equation from Reynolds' transport theorem. Here's Reynolds' transport theorem, with E subbed in for the intensive property B. The first term in this, which is equal to the rate of change of energy in the control volume, will equal 0, since this is a constant and we are taking the derivative of it. The second term has an aspect of it, which is the density times the velocity times the area. This part is equivalent to the mass flow rate, so we can also sub in the mass flow rate for that term. E, which is equal to the energy, can be written as the internal energy plus the kinetic energy plus the potential energy, and we will also sub that into our equation in order to yield the equation at the bottom. This equation can be simplified further by subbing in the enthalpy for the pressure out over the density plus the internal energy. This gives us our final simplified power equation at the bottom of this page. Now we can, in our particular problem of a hydroelectric dam, we can cancel out a few factors. First, the velocities will cancel out. The pressure, because it is an open jet, will be 0, and the pressure at the top of the reservoir will also be 0. This gives us the following equation. The first term in this equation is equal to the rate of work done, work lost. The second term is equal to the rate of work done by the fluid. And the third term is the rate of work done by the turbine. These equations can be used to solve for the values we are looking for. We were given both the height and the flow rate, which can be subbed into the rate of work done fluid equation, and which gives you a value of 119.1 megawatts for the work done by the fluid. The work lost is equal to the work done by the fluid minus the work done by the turbine. And since the work done by the turbine was equal to 100 megawatts, we have 119.1 megawatts minus 100 megawatts, which gives you a engine work lost of 19.1 megawatts.
Ring, ring, hello?
Just a
Ring,
word
ring,
of advice
hello?
to our viewers.
Ring, ring,
whenever you
hello?
make a jam, all you gotta do is
Ring,
call
ring,
for me.
hello? Ring,
You
ring.
have a bad connection.